Have you ever stopped to think about what's really going on inside your phone when you take a picture, or how a song gets from a server to your headphones? It all boils down to something incredibly simple, a tiny switch that's either on or off. In this explainer, we're going to pull back the curtain and see how billions of these little switches create our entire digital world. So that's the million-dollar question, isn't it? How on earth do we get from a basic on or off signal to the rich, complex, colorful things we see and hear on our screens every day? That's exactly the puzzle we're going to solve together. All right, here's our game plan. We'll start with the absolute basics, the computer's native language. Then we'll figure out how to translate our world into that language. After that, we'll see how this stuff pops up in real life. And finally, we'll look at how we manage to shrink it all down to a manageable size. First up, let's talk about the computer's native tongue. We're diving deep, right to the very core, to figure out why absolutely everything in a computer's world is just a bunch of zeros and ones. And that language is called binary. You see, at its heart, a computer's just a massive collection of microscopic switches, millions of them. Each switch has only two jobs. It can be on or it can be off, and that's it. We use the number 1 to represent on and 0 for off. This is the only language the hardware actually understands. Okay, so computers speak in ones and zeros. Got it. But we humans use numbers like 10 or 25 or 39. How does a computer understand our numbers? Well, that's where translation comes in. Let's see how it works. We're going to walk through a quick example here. The number system you and I use every day, with the digits 0 through 9, that's officially called the denary system, or base 10. So let's take the denary number 39 and translate it into the computer's language, binary. All right, the method here is actually just a bit of simple division, over and over again. So first, we take our number, 39, and divide it by 2. That gives us 19, with a remainder of 1. We hang on to that remainder. Now we take our new number, 19, and do it again. 19 divided by 2 is 9, with a remainder of 1. Keep going. 9 divided by 2 is 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0. And one last time, 1 divided by 2 is 0, with the remainder of 1. We stop here because our main number hit 0. Now for the big reveal. You take all those remainders we saved and you read them from the bottom to the top. So starting from that last one we got, we have 1, 0, 0, 1, 1, 1. And boom, there it is. The number 39 in our language is 100111 in binary. Now the computer knows what we're talking about. So, as you can probably imagine, writing out these long strings of ones and zeros would get old really fast for a human programmer. It's just a lot to look at. That's why we have a clever shortcut called hexadecimal. It's a base 16 system, so it uses our normal 0 through 9, but then adds the letters A through F. The really cool part, a single hex digit can stand in for a group of 4 binary digits. It just makes everything shorter and way easier for people to read. Okay, so numbers are sorted, but what about everything else? The photos, the music, the text messages that make up our digital lives. How does all that get squished down into a stream of ones and zeros? Well, for text, computers use a kind of codebook. The old standard was called ASCII. It used 8 bits for every character, which was plenty for the English alphabet and basic symbols. But then the world got bigger. We needed emojis. We needed characters from other languages. That's why we have Unicode now. It uses 16 bits or more, giving it space for over 65,000 different characters. So your smiley face emoji, it's really just a unique string of ones and zeros, thanks to Unicode. Now, what about sound? For that, we use a technique called sampling. Picture a sound wave moving up and down. A computer takes a snapshot of that wave at thousands of tiny regular intervals. For each snapshot, it measures the amplitude, basically the loudness, and records that value as a binary number. String all those numbers together, and you have a digital song. And images. Well, if you zoom in really close on any digital photo, you'll see it's just a giant grid of tiny little dots. We call those pixels. Every single pixel is a specific color, and that color is stored as, yep, you guessed it, a binary number. The number of bits we use to describe each pixel's color is called the color depth. More bits means a bigger box of crayons to choose from, which gives us more colors.
Okay, this all might sound a little bit like we're stuck in a math class, but I promise, you see this stuff every single day. So let's step out into the wild and find some of these concepts in the real world.
Remember hexadecimal, that convenient shorthand for binary? It's everywhere. Ever had a program crash and give you a bizarre error code? That was probably in hex. Your phone has a unique ID called a MAC address. That's in hex. But my favorite example is on the web. Every single color you see on a website has a specific hex code. That bright, classic red, that's just hashtag FF0000. It's a lifesaver for web developers. Now here's a really interesting problem that all computers have to deal with. They can only handle a fixed number of bits at a time. Think of it like a small bucket that can only hold, say, 8 bits of information. What happens if you do a calculation and the answer needs 9 bits? Well, the bucket overflows. That extra 9th bit just gets dropped. It's gone. This is called an overflow error, and it's one of the fundamental limits of how computers work. So as you can probably tell, using all these bits to represent our world creates some seriously huge files. A high-quality photo or long song can take up a ton of space. This brings us to our final topic, how we shrink that digital universe down using something called compression. And to really get why we need compression, the math is pretty simple. The size of an uncompressed image is just its resolution. That's the total number of pixels, multiplied by its color depth, which is the number of bits for each pixel. A modest photo could easily be 24 million bits. That's a big file. And for high-def video, the numbers get astronomical. That's why compression isn't just nice to have. It's absolutely essential. So how do we do it? Well, there are 2 main flavors of compression. First, there's lossy. This is what JPEGs and MP3s use. It makes files way smaller by permanently throwing away data it thinks we won't notice, like sounds that are too high for a human to hear. Then there's lossless. This method doesn't throw anything away. It just finds a more clever, efficient way to write down the data. The original can be perfectly rebuilt, but the file doesn't get quite as small. And here's a pretty good way to remember the difference. You can think of lossy compression as lousy compression. Why? Because once that data is lost, it is gone forever. You can't get it back. So let's bring it all home. The next time you save a photo or stream your favorite song, just think about what's happening under the hood. Which type of compression is being used? And what's the trade-off you're making? Perfect quality for a tiny file size? It's a choice we make every time we hit save. Thanks so much for joining me.